In this video I want to show you how you can scale a differential equation by using dimension analysis. You need to know how to calculate pi factors, so make sure to watch at least my video guide about calculating pi factors if you have problems regarding pi factors. Now let's take a look at the following differential equation. Our goal is to bring this differential equation in a nicer form, so it's easier for people to work with it. We will accomplish this by bringing it in a dimensionless form. So here on the left we have our original differential equation. We want to know how to scale this differential equation so that it looks like this here. Especially we want to know how to define the variables y, tau and the constant a, so we can accomplish this form here. We need the pi factors for this. To calculate the pi factors we have to think about all the quantities our problem depends on. In our case we have given a differential equation, so these quantities can be found by looking at our differential equation. So we have the following quantities. We have the position x, we have the time t, so x and t, we have the gravitational constant g, we have capital R, which is some kind of a radius, and we have the starting velocity v. Okay, here on the left we have to write all the basic dimensions our quantities here depend on. So we need the dimension of a length, we need the dimension of a time, and we need maybe the dimension of a mass. Okay, and here we have to write the dimensions. So x is a position, so we have 1 time length, 0 time, 0 mass. T describes a time, so 0, 1, 0. G is the gravitational constant, which is a acceleration, so we have 1 minus 2 for the time and 0 mass. R is a radius, so it is 1 times length, 0, 0, and v, the starting velocity, is a velocity, so 1 minus 1 and 0. It can be seen easily that this matrix here is of rank 2. So the next step is to choose 2 linear independent columns of this matrix here. I already told you in my other video that you have the freedom of choice, but this choice here will affect the scaling results. So the way the scaled differential equation will look like in the end. To get this result here, you have to choose the columns with R and V. We will talk about this again later on. Also, you shouldn't choose the columns with X and T. We want to transform these variables in a dimensionless form. You will see what I mean in a minute. So let's choose the columns of R and V in this example. Now we have to write the columns of X, T and G as a linear combination of these two picked columns. Let's do this. So we have to write 1, 0, 0, which is the X column, as a linear combination of these two picked columns. This is pretty easy because this is 1 times 1, 0, 0. And this here is the R column. So the next column is the T column. So 0, 1, 0, which is the T column. And we have to write it as a linear combination of these two columns, which is also pretty easy because this is -1 times 1 minus 1, 0 plus 1 times 1, 0, 0. So this here is the V column and this here is the R column. And the last column is the G column. So 1, -2, 0, which is the G column. And we have to write it as a linear combination of these two columns. So this is 2 times 1 minus 1, 0 plus -1 times 1, 0, 0. This here is the V column and this here is the R column. So now we have written these columns here, X column, T column and G column, as a linear combination of these two columns here. Now we can write down the pi factors. We will also give them new names. So the first pi factor, pi1, which we will call y, is equal to, so x times r to the power of -1. So this here is the first pi factor. The second pi factor, pi2, which we will call tau, is equal to t times v to the power of 1 times r to the power of minus 1. The last pi factor, pi 3, which we will call a, is equal to g times v to the power of minus 2 times r to the power of 1. So these here are the calculated pi factors. Now we will use these factors, especially the newly defined variables y and tau, to scale our differential equation. The idea is to get rid of the old variables x and t in our differential equation and replace them with the dimensionless variables y and tau. To do this, we have to differentiate y with respect to the new variable tau. Okay, so we have to differentiate y with respect to tau. So let's write this down. So the first thing we have to do is to replace this y here with x times r to the power of minus 1. So we have replaced this y with this here. Okay, the next step is a little trick. So the idea is, in the end, we want to have something that is differentiated to the variable t. So we have to bring in this dt here again. To do this, we write it down like that. So this here is just 1. So we can write it down like that and nothing is changed. And now we have this dt in the equation again. Let's write this down again in a little bit different way. So we write it down like that times Now this here says that we have to differentiate the variable t with respect to tau. From this relation here, we get that t is equal to r v tau. So from this relation here, we get this relation for t. And now this here says that we have to differentiate t with respect to the variable tau. When we do this, we get r to the power of -1. When we differentiate t with respect to tau, we get this factor here. And this here is not changed. This here is that. So here we have differentiated t with respect to tau. Okay, now we write it down one last time. This is 1 d So when we differentiate y with respect to tau, we get something like this here. Now we have to differentiate y with respect to tau again. So we have to calculate this here. So we can write this like that. And we already know what this here is, because we have calculated here. So this here is that here. Okay, so we insert it here. And get this here. So to get rid of this d tau here, we use our trick again. So and this here. So this here is just 1. So we can write it down like this here again, because nothing is changed. And now we write this down again a little bit different. So okay, now we have to differentiate t with respect to tau again, which is this factor here. So in the end we get this here. Now we take a look at this here, the second derivative of x with respect to t. And now take a look at the differential equation. We already know that the differential equation fulfills this here. So this here is the differential equation. So the second derivative of x with respect to t is equal to this here. So we can insert this here here. So let's do it like this. Copy, paste. So this here is that, and we get it from the differential equation. So now we have to get rid of this x here and replace it somehow with y. But this is pretty easy because we already know from this relation here that x is equal to r times y. So we can just insert this here for x, and we will get this minus, we will write here. So we insert this x here, so we get y r plus r squared. Now we bring this r outside here, which leads to, so we can do it like that. So we get minus g, and this here is 1 y plus 1 squared. And now let's take a look at this factor here. We already know what this here is, because this here is a. So let's bring it down here. So when we compare these two things, so here we have a, and this here is this factor here, and we see it's the same. So r, g, and v to the power of -2. So this here is just a. Maybe we can do it like this. Okay, so now we get this here. Now this here is our new scaled differential equation. Let's write it down again. Okay, but when we take a look at the original differential equation, we also have boundary conditions, and we have to calculate them too for the new variable y. So we have to find out what y at the point 0 is, but this is pretty easy because we have this relation here. Just so y at the point 0 is just x at the point 0 times some factor r to the power of -1. So y at the point 0 is just 0, because x at the point 0 is 0. So here is 0 times r to the power of -1. So this is 0. And then we have to find out what y differentiated with respect to tau at 0 is, but we have already calculated this here, because from this here we know that y differentiated with respect to tau is equal to that here. So this here is 1 v at the point 0, and we know that this here is v, because this here is that here, and this is 1. So this here is our new differential equation, which is scaled and dimensionless. So this here is the differential equation, and here we have the new boundary conditions. When you have to work with the differential equation, you can always use the scaled differential equation. So you can do all your calculations with the new variables y and tau, and in the end, when you are done, you can go back to your original variables x and t using these relations here. Okay, I want to talk about one last thing. As I told you before, choosing another pair of linear independent columns at this point here leads to different pi factors and therefore a different scaled differential equation. So instead of picking these two linear independent columns, we can, for example, pick these two columns, or these two columns. Let's try it out. So instead of these two columns, we can, for example, choose these ones. So the G column and the v column. The next step is to calculate the pi factors. So I've already done this here and also gave them new names. So the first pi factor z, the second pi factor t, the third pi factor c, and I already calculated them. You can try this out yourself if you want to calculate these pi factors. Okay, let's scale this differential equation here using these new variables. So we have to calculate this here at first. So inserting for this set here, this here. So we have and now we have to use the trick again, where we have to differentiate t with respect to capital T. So we need t is equal to this here, and we have to differentiate t with respect to capital T. So we get the following thing. So this here is when we differentiate small t with respect to capital T, we get this here. And then we have this here and that here. Okay, we write it down one more time because this here is gone, and here we have the following. So then we have to differentiate it one more time. So we get this factor here again because we have to differentiate t again with respect to capital T. So in the end we get the following. Okay, and now we can insert the differential equation here. So we replace this here with that here. Let's do it like that. And we also have this factor here, or g. This goes away. And so we have this here without the g. And now we want to get rid of this r here. So we try to bring this r outside of this. So we do it like that. So we have r times plus 1, this squared. So this is the same. So we can bring this r out again. So this here is gone. Okay. And now in the end we also have to replace this x here. So for replacing this x we use this relation again. So x is equal to z v squared g to the power of -1. So inserting this x here, we get 1 v squared g r. Is this correct? gr z plus 1 squared. And now let's take a look at this factor here. We have this factor here and we called it c. So this is r v to the power of -2 g, which is the same here, but we have to take the inverse of c. So these numbers here are with a minus sign here. Okay, so this here is 1 c minus 1 z plus 1 squared. So we have this new differential equation here, and we also have to think about the boundary conditions. So z0 doesn't change, it's still 0. You get this from this relation here, and this here you can calculate by using this relation here. So you have to find out what x differentiated with respect to t at the point 0 is, but you already know this. This is v, so you get 1 again. And this here is now our new differential equation with the new boundary conditions here and there. I think I have forgotten the minus here, so let's fix this quickly. Okay, I hope this video was helpful and showed you the basic concepts of scaling a differential equation. If you want to try it yourself, you can, for example, choose these two columns here, and after that try to calculate the pi factors. Then you can define new variables like here, and then use these variables to scale the differential equation.